طيب السلام عليكم ورحمة الله وبركاته. Good morning everybody. Today we would like to welcome Dr. Shafiul Alam. Dr. Shafiul Alam, he is currently a research engineer 3 at the Applied Research Center for Environment and Marine Studies at KFUPM. He was also before for more than 2 years as a postdoc at K.A.CARE Energy Research and Innovation Center at KFUPM. And he has also long experience in different universities. His research interests include energy and environment, power to gas system, AC/DC microgrids, energy storage system, machine learning and optimization. He received before a couple of times Best Paper Award in different IEEE International Conferences. In addition, he has published more than 60 research articles in ISI journal and many conferences. So Dr. Alam today will talk to us about DC microgrid voltage control and energy management. As you're aware, this is important topic. Microgrid is, or let me say in general, there are high potential to have more decentralized stations. So microgrid is very well associated with decentralized power stations. For that reason, it is important to know what is microgrid, what is energy management, what are the common challenges around that. So now I would like to open the discussion and the presentation first, of course, to Dr. Shafiul Alam to start his presentation. تفضل دكتور شفيع العلم.
Assalamu alaikum wa rahmatullahi wa barakatuh. Thank you, Professor Dr. Fahd, for your nice introduction. Inshallah, today I will be talking about DC microgrid voltage control and energy management. First of all, the presentation outline in today's talk, actually mainly first I will discuss about the energy challenges and several solutions from the broad perspective of the energy. Then I will be discussing specifically the electrical energy, including the renewable energy, several challenges and solutions. I will be discussing about this topic. Afterwards, I will show the global investment and generation from the renewable energy sources. Then, in order to facilitate the integration of the renewable energy, we need a large number of energy storage devices. So I will give a brief introduction on energy storage devices. After this, I will introduce net zero energy building system to facilitate integration of renewable energy as well as the energy storage devices. Then a case study of DC microgrid will be considered in today's talk. Finally, I will, after introducing the DC microgrid, I will talk about a new voltage control and energy management technique for the DC microgrid. Then I will show the implementation results and discussions. Finally, the conclusion of this work. So let us see the energy, challenges. If we consider the energy from broad perspective, we have different sources of energy. Definitely, we have the this fossil fuel-based energy, for example, petrochemical, natural gas, coal, and so on. And for the energy system, we have numerous challenges. For example, the energy security. One is the energy security. We have to have a good supply system, secured supply system. We have to have a reliability. Also, there are some challenges related to economic productivity. For example, the growth in demand will have impact on the energy system. Also, price volatility will have impact on the energy supply system, energy reliability. Also, there are some environmental issues. When we are using the energy sources, maybe any kind of sources, we are using definitely the land, we are using the water. Also, if we are using any kind of fossil fuel, so there will have some carbon emissions. So there are some environmental impacts. So all these imperatives must be addressed for a reliable energy system. Now, if we see the, if I specifically consider the electrical energy system, there are some challenges as well. For example, electrical energy, especially if we are generating energy from the fossil fuel, so we have some challenges, and these challenges can be overcome with many, technological advancement. For example, we can take the initiative to improve the energy efficiency for the load, for the generation system, for the transmission system, for the distribution system, any. So we can have some, initiative to improve the energy efficiency. We can also integrate the, renewable energy for the with the electrical grid. So it will definitely solve many challenges for the many problems of the electrical energy system. Also, we can use next generation nuclear energy system. Also, as we know that the most of the electrical energy sources are distributed in nature. So, for example, a building normally consumes the electricity. Any building or any load center normally takes the electricity from the grid. However, since this, the electrical energy is distributed in nature, if we can generate the electricity from the load center and we can integrate with the grid, so it will, have some positive impact on the electrical network. Also, we can have the option for demand side management. Demand side management means the system operator has the, flexibility and the opportunity to control the load. So in this way, we can also have some good impact, and we can solve many problems related to the electrical energy problem. Now, for the renewable energy, as I talked before in the last slide, so for the renewable energy system integration, we have several opportunities, several advantages. For example, if we consider the renewable energy, definitely this is clean alternative to the fossil fuel. Also, it has zero or very, we cannot say the zero, but definitely we can say it has very low operational cost for the renewable energy system. Also, it has less maintenance cost compared to the conventional generation system. The synchronous generation generator system. Also, it helps diversify the energy supply system. It means that we solely don't depend on the conventional fossil fuel based electricity generation. When we are integrating more renewable energy, it will diversify the supply system. And it also helps to get the environmentally friendly energy source. We can get the environment friendly energy source from the renewable energy sources. And it has several downsides as well. For example, it is intermittent in nature, and it is very difficult to predict the how much generation will get from the renewable energy sources, especially if we consider the wind system or solar system. So due to the variation of the sunlight and the wind speed, so it is very difficult to predict the output from these sources. So it is due to the intermittent nature of the renewable energy sources. Also, for the renewable energy sources, we mainly connect most of the renewable energy sources with the these power electronic converters. So these types of converter, when we are integrating more renewable energy, it means that we are disconnecting this conventional synchronous generator from the system. So what will happen there? So when we are integrating more renewable energy, more power electronic based generation system, so we are removing the synchronous generator. So it will reduce the overall inertia of the power system. So it will have very negative impact on load frequency control. So due to this inertia issue. So this is another very challenging problem for the renewable energy integration. Also, it has complex control structure. It means that when we are integrating the renewable energy, so we need to control all the power electronic converters. We need the mathematical model for the converter, for the energy sources, for the loads. So we need a complete mathematical model to design the controller. Also, it has expensive installation cost, especially if we consider the PV system. We have huge installation cost for the PV system. Now, if we see the worldwide renewable energy investment in dollar, if we see in this figure that till year 2010, most of the the investment was more for the wind system compared to the solar system. However, after this year, after 2010, the scenario has been changed. So more investment has been observed in billions of dollars for the solar system compared to the wind system. And this is the cumulative, global cumulative installation. Actually, I'm mainly focusing on the wind and solar. So we see the gigawatt power generation from the solar system worldwide. And this is the cumulative. So if we see until, actually in this figure, we have till year 2021 from 2000, we have this actual scenario. And for the year 22 and 23, we have the projection, or we can say the forecasting. So we see until the year 2019, so total power, I mean the total gigawatt power generation from the wind was higher. But after that, after year 2019, the scenario has been changed. So more power has been generated from the, from the solar system. Let's move forward. Now, as I discussed before, that when we are integrating the renewable energy system, so it will reduce the overall inertia of the system. So in order to support the inertia of the system, and in order to facilitate or in order to accommodate more renewable energy, what we have to do, we have to install a huge number of battery and supercapacitor or any kind of energy storage devices to support the inertia of the system and to make the system balanced and reliable. So if we consider, for example, the battery system, for the battery, it has high power density, high energy density. It means that the battery can provide, energy or power for a very long time. Also, it has a low power density. It means that battery cannot ramp up the power. I mean, it cannot provide the huge amount of power within very short time. So this is the downside of the battery. Also, it has the lesser lifespan by the number of charge cycles compared to the other energy storage devices. Now, if we consider the supercapacitor, so for the supercapacitor, we have the high power density. It means that supercapacitor can, speed up the power, or supercapacitor can provide the, huge power within very short time. On the other hand, the downside of the supercapacitor is that it has low energy density. It means that it cannot provide the power for the long time. Also, it has the longer life cycle. So if we combine these two, I mean battery and supercapacitor, so we can say that hybridization is a good solution for the implementation of the, or for the accommodation of the renewable energy with the grid, or maybe in the islanded operation, whatever. So if we use the energy storage devices, in that case, we can say that the hybridization of the battery and supercapacitor is a potential solution to the problem. And if we move forward for the integration of the renewable energy, one of the best way to integrate the more renewable energy is to implement the net zero energy building. And this concept has been evolved recently, and this is in many European countries, for example, Germany, Denmark, and some other countries, they are focusing more on the net zero energy building. So the we can define the net zero energy building like that: the building generates at least energy as it consumes. Or we can say alternatively, if we consider the environmental impact, the building can export the energy, at least export the energy as it, I mean the energy from the, from the emission, it gets from the emission-based energy generation system. So it generates the same amount of energy or greater energy from the emission-less energy, from the, from the renewable energy sources. So in this way, we can have the, positive environmental impact. So to achieve the net zero energy building, so we have we have to take several, initiative, or we have to do some, work to have a net zero energy building. We have several aspects. For example, we have to design the energy infrastructure, and for the energy infrastructure, we have the electrical energy system, or we can connect the electric. We can connect the net zero energy building with the grid, so that we can export the surplus energy to the grid, or we can import the deficit energy when we have the deficiency in the energy in the building. So we can import the energy from the grid. So we have to have the electrical grid connection. There are some gas pipe network also with some net zero energy building system. So the concept is that now it has a great talking about the this power to hydrogen. So in this case, when we have the more renewable energy, sometimes maybe grid is disconnected or the price of the electricity is less. So in that case, the electricity can be used to generate the hydrogen. And this hydrogen is called the green hydrogen. So from the renewable energy, we are generating the hydrogen. So this hydrogen can be injected to the gas pipe. So we have the gas network. Also, we have the district heating and cooling system. We can also consider the biomass distribution system network, also energy storage devices. So these are the structure related to the energy infrastructure. Also, we have the renewable energy sources. We may have for the building. We have this is called the building and integrated PV system, BIPV. So we can connect the PV system. It may be the offsite PV system. We can generate the PV from the rooftop PV panel, or from the wind turbine, or we can have some provision to generate the electricity from offsite, very close to the building. So we can generate the electricity from the renewable energy sources. We can also have the biomass CSP system. For the energy efficiency measurement, we have to design the building. We have to design efficient building, and we have to the building should be in such a rotation, or in such a direction, so that we can get the direct sunlight, or we can have the wind speed, high wind speed for wind generation. We can have efficient HVAC system, heating, ventilation, and air conditioning system. We can have efficient appliances, efficient control technique, and also the behavior of the occupant. I think you are getting my point. So when we are, depending on the behavior of the occupant of the building, so energy efficiency can be also improved. So these are several aspects to achieve the net zero energy building. So now I will move forward to the next slide. So now, one of the best way to achieve the net zero energy building is to implement the microgrid. So now I will be mainly focusing, I will be moving to the main topic of today's discussion. So we have the microgrid. Let us consider this microgrid. We have the PV system, we have the battery, supercapacitor, all are connected with the DC-DC converter to the DC bus. We have also some DC loads, which is directly connected to the DC bus. And if we are connecting this DC microgrid with the AC, so we have to have a bidirectional voltage source converter, or AC-DC converter, any inverter, and we can have some residential load, AC load. So this is a microgrid. So this microgrid concept can be implemented to achieve the net zero energy building. And if we specifically consider the DC microgrid, we have several advantages. For example, it can facilitate easy integration of renewable energy sources, especially the solar system, because the solar PV system has the DC output. So we can directly connect this DC output to the DC bus. So we need only a converter. We need only a boost converter. On the other hand, for the PV and battery system, we can use only the DC-DC converter. We don't need AC-DC converter. So it facilitates integration of the energy storage devices, also the PV system for the DC microgrid. Also, there is no frequency control and reactive power compensation issue with the DC microgrid. However, there are some challenges still with even with the DC microgrid. We need a complex mathematical model to design the controller. We have to control the DC bus voltage, because some of the loads, DC load, they are very much voltage sensitive. If the voltage changes, it does not function properly. So we have to have some complex voltage regulation for the DC bus system. Also for the energy storage devices, we have to control the limit of the charge. It means that we have to, for example, for the battery, it has maximum charging limit and minimum discharge limit. This is called the depth of discharge. So we have to control the charging and discharging of the battery within a certain limit, within a certain state of charge. Also, we have to make the balance of the system. So we have the different sources, we have the different loads. So what we have to do? We have to make a balanced system by proper energy management algorithm. So these are the challenges. Now let us consider a specific DC microgrid, which I have considered in my study. So we have a battery and supercapacitor. We have a grid connection with the voltage source converter. We have the distributed generator. here I am terming the PV or wind system as a generalized one, as a distributed generator, because the PV or wind can be operated as a distributed generator. So I am now mainly, talking the distributed generator instead of the PV or wind system. So this is a distributed generation system. We have a load. This is a resistive load. So this can be varied, and we have also a constant power load. So it means that this is a small microgrid, but it considers all the possible combinations of the sources and loads. So if we can implement this practically, or if we can implement, we can control the voltage and energy management for the system. So we can control the voltage and energy for any large system. So it consider almost all dynamics of the DC microgrid. Now let's move forward. So for the controlling, so we have to design the controller for all these energy storage devices, for the DC, for the constant power load, and for the grid. So I will now mainly introducing the different control for this system. For the DC, if we consider the DC, we are considering a reference power for the DC, and we are converting this power to the current, and after this we are comparing the error of the current and processing by the PI controller. This is the simplest controller because this is the not the main contribution of this today's discussion. Also for the constant power load, we are controlling the voltage accuracy. If we go back for this, if we see here, this is a resistive load, it is constant, and if we can control the voltage here constant, so it will emulate the a constant power load. So our objective is to control a constant voltage here across this load. So to control this voltage, so we are comparing the reference voltage with the measured voltage, and then we are processing with the PI controller to generate the gate pulse. So these are the simplest control for the DC and the CPL. However, we can consider the complex model for the PV or wind system, but for this work, the main focus is controlling of the energy storage devices and to energy management. So I will be mainly discussing about that point. Now, let us consider the battery and supercapacitor from and its equivalent circuit. We have the battery, we have the supercapacitor, and if the total current shared by the battery and supercapacitor is I load, so this the amount of the current shared by this battery and this supercapacitor. Now we can write the Droop equation for this one. So this is the Droop equation for the battery. So this is given by the first equation, and afterwards, for the capacitor, we have introduced this called the capacitance Droop control. So this is a contribution. So we have introduced the capacitance Droop control. So after simplifying these two equations, we have this, the equation for the current. This is the output current for the battery, and this is the output current for the supercapacitor, and this is the total load current. So if we see these two transfer function, the nature of these two transfer function, this is a first order transfer function. This is we can say a low pass filter, and this is a high pass filter. So if we take the step response for these two transfer function, so what we see here, interestingly, so if we see that the current is if a step change in current, so what is happening? The battery is gradually, initially it provides zero current, and then gradually goes to the, this steady state current. So it means that initially when there is high frequency components, it provides zero current, and then gradually it goes to the steady state current. On the other hand, if we consider the supercapacitor, ISC out, this ISC out, so what we see here, the battery is supercapacitor is providing the maximum current at the transient condition, and then gradually it's going to the steady state condition. So in this way, the current between the, the power or current, whatever we say, can be split into high frequency component and the low frequency component between the battery and supercapacitor. So the battery can provide the steady state current, and the supercapacitor can provide the, this transient current. Now, this control till this now, this is this one of the goal has been achieved by splitting the current, but still we have some problem. This is the Droop control, so it will have the voltage deviation. So what we have to do, so we have introduced this this voltage shifting term here, sorry. So if we see here, we have introduced this voltage shifting term, delta V. So for this delta V, we have we have processed this voltage. I mean, we have measured the voltage, battery voltage, and we have measured the capacitor output voltage. And this is processed average of this voltage, and we subtract from the nominal voltage, and we get this voltage deviation term after processing it with the integrator controller. And after simplifying all these equations, we get that this output voltage equation and this the current sharing equation. From this equation sets, we generate the final control for the supercapacitor and battery. So this is the droop control, this is resistance droop control, and this is the capacitance droop control. And we have two control loop here. We have the outer voltage control loop and inner current control loop. So we have designed the controller parameters with systematic way with some techniques. And then this is the control for the supercapacitor. Definitely here we have the same similar operation. We have the outer voltage control loop and inner current control loop. Now this is the control for the grid VSC. So for the grid VSC, we have to control we have the outer voltage controller and we have the inner current controller. And for the grid VSC, we have used the conventional control technique for this is called synchronously rotating Q frame control. So we have for the D and Q axis, for the current control, we have the direct axis current control and we have the coordinator axis current control technique. And then we generate the gate pulses. We have also the PLL, as the guys who are working on control technique, they know this, that these are the well-known control technique for the controlling for the voltage source converter. Now this is the proposed energy management algorithm. So we have several measurements, and from the measurement we calculate several power and current and so on. Afterwards, we decide either the grid, microgrid, this DC microgrid is grid connected or not, depending on the current. This is the simplest one. We can, however, we can use any other advanced technique for the detecting the islanding of the system. So afterwards, we consider, we check the power of the battery. Either this is charging or discharging. If this is discharging, so minimum discharging limit is 45%. And if it is charging, maximum charging limit is for 95%. And afterwards, either if it is within the limit, there will be no action. If there is, it's going to violate the 95%. So we have to, coordinate with the distributed generation system, either ramp up or ramp down to keep the, charging within 95%. Also, this is for the lower limit state of charge control. So if this is within the limit, so no action. If this is going above the, for example, the limit, so in that case, either if the PV or the distributed generation, if it is in maximum limit, so what we have to do if this is greater than maximum, so we have to shed the load. If not, then we can, in that case, we can ramp up the DC power output. So this is the control for the islanding, and this is the control algorithm, management algorithm for the grid connected mode. Now, this is the implementation for the proposed control technique. So we have used the real-time digital simulator for the implementation of this system, DC microgrid system. So we have built the DC microgrid with the RTDS environment. Also, we have developed the controller with the DSpace. So RTDS has the option that we can, we can export and import the signal with the digital input output and analog input output cards with the RTDS. So it facilitates, the real-time operation, and we can test the any system, any controller, any protective devices with the RTDS. So we implement the system with the RTDS and we implement the controller with the DSpace. And this is the complete setup for the RTDS and DSpace implementation for this proposed control technique. Now, this is the results. We see that in this figure that initially the battery power is negative. It means that battery is charging. So afterwards, when the scenario changes, so battery provides the steady state power gradually, but it goes gradually. But initially, the supercapacitor power is 0, so it provides the transient power, and then it comes back to 0. And again here it's providing only the transient power. So in this way, we can split the power between the high frequency and low frequency components, so that the battery provide only the steady state power and supercapacitor only provide the transient power. And if we see the load power here, this is the resistive load power. This is the resistive load power. This is almost constant, except for this, except for this, this called transient period. So except this transient period, this is controlling perfectly the resistive load power. And for the constant load power, we can say that this is perfectly, we can say this is a constant 1 kilowatt power, except this, very small transient here during the voltage changes in the system. And this is the total power. So total power is mainly this constant power is reflected to the total power. I mean, this resistive power is reflected to this total power. And now let's see the state of charge. So for the state of charge of the battery, so initially the battery is charging. So when it is around 0.95, so the battery starts to discharge gradually. So when it comes to the minimum level or around the minimum level, so it goes again, it starts charging. On the other hand, for the supercapacitor, we see it automatically controls the state of charge. We don't need any additional controller with the proposed control technique. So the supercapacitor, we consider the initial state of charge is 0.5 or say 50%. So then it deviates or it provides the power during the transient period. So it's deviates from the its nominal state of charge, and then it comes back again to its nominal state of charge. Also, there is transient here to provide this transient power. And the DC-link voltage, the proposed control technique, we said that DC-link voltage is tightly regulated to the 400 volt, and only there is very small deviation for a transient period, even a fraction of second like this. Also, there is a there is deviation for this DC-link voltage. And we have also compared the proposed technique with the conventional control technique. For the conventional control technique, we see that there is a huge voltage deviation for the DC-link. However, the proposed control technique, so we are able to control the DC-link voltage properly, except this transient variations. So the proposed control technique is capable to control the energy of the system, to make the system balanced, to make the energy split between the battery and supercapacitor. Also, it facilitates, or we can say it can improve the DC-link voltage deviation. Now, let me go to the conclusion of this talk today. So in this talk, I have discussed about the energy from a broad view, and then I have specifically discussed the renewable energy sources. And after electrical energy and renewable energy system, I have also discussed the energy storage devices for integration of the renewable energy sources. And then I have discussed the microgrid system and the net zero energy building system for integration of the this energy storage devices and the renewable energy. And by the way, as we know that the net zero energy building is a grand challenge for the King Fahd University of Petroleum and Minerals. So this work, the implementation of the DC microgrid can facilitate, implementation of the net zero energy building with the KFUPM campus. And that's the end of this presentation. And thank you all for attending this presentation and this talk today. Thank you. Now,
thank you, Dr. Alam, for the well presented material. I would like to open the floor for our colleagues. If there is a question, please raise it. You can raise your hand or send your question. Maybe some of you will have difficulty to talk. Is there a way to allow them to talk?
Doctor, I don't know. There is a Doctor, should I allow all? But
okay, it's fine.
I am trying to allow all.
طيب, if you allow me, Dr. Alam, I have a question now.
Yeah.
The approach you presented.
Yeah.
How do you think it will be implemented in real application? Do you think still it is relatively mature, or still it needs more R&D?
Doctor, I think we can implement this system. Definitely, I think this is a matured. I mean, we can implement the system, this proposed technique, because if we are considering the net zero energy building system, and if we are going to integrate the renewable energy, so in that case we have to we can integrate this as a DC microgrid, as I mentioned in the talk. And for the DC microgrid, two main aspects is to control the power and the voltage. So I have presented in this talk that we can definitely easily control the power and voltage for the DC microgrid system. So we can definitely implement this system if we have all the facilities. If we can have some control, the control design technique, and if we have some controllers, so we can definitely integrate such controller for the DC microgrid.
Excellent, Dr. Alam. Is there any question from the attendees?
Assalamu alaikum.
Alaikum salam, tafadhal.
I am Ayman Masmali. I want to ask about the control schemes. So for this DC grid, is this multi-input, multi-output system? So how is the block diagram, the control block diagram would look like? And I would like also to hear about the control schemes and advanced control. Like, is there any advanced controls for the DC grid, like fuzzy logic or MBC, model predictive control, and other advanced controls? Thank you.
Regarding your first question, yeah, definitely this is multi-input and multi-output system. For example, we have different, if I go back to the, sorry, let me. So if I go back to the controller here, okay. If we see here that we have different sources. For example, if I consider the DC output, DC controller, we have the reference DC power. Also, we have the reference, the measured current from the DC. Also, we have the measured voltage from the constant output, constant voltage. Also, for the for the battery super capacitor, we have different input signals. So we are sensing the input from the different, different parts of the system. So we have the different input, and then we are processing this with the controller, and we are connecting, and we are generating the output for the controller. So this we can say definitely a multi-input, multi-output system. And regarding your second question, as you know, for the DC microgrid, there are different texts. Yeah, definitely, I saw some papers and some articles related to the fuzzy logic and MPC control. But the most simplest control and most used control in the DC microgrid is called the decentralized control. One is, for example, the centralized control, decentralized control, hierarchical control. There are different ways to control. Actually, it depends on the design, how your your system, your resources are located. So depending on your resources, depending on your planning, so you can choose any control technique. But in this talking, actually I am mainly talking about the decentralized control technique. So I think I have answered your question.
Yes, thank you, Mr. Alam. Maybe another question. If I want to apply this advanced control, so do I need to concentrate on a single controller, or I have to go for the whole system?
Okay, so for example, you talk about the MPC, model predictive control. So one good thing for such type of control, even for the model predictive control, you can consider the model predictive control in decentralized manner. I mean, for example, for the battery and supercapacitor, you can use the model predictive control. But for this one, you need the complete mathematical model. As you know, you have to do some optimization for the model predictive control. This is not the something like the PI controller. So you have to have some optimization technique for the several. You have an objective function to generate the gate pulse for the MPC. So you can do this. I mean, you can implement any advanced control technique. For example, if I consider the MPC, so you can do it in a decentralized manner as well. I think I answered your question.
Yeah, sure. Well, thanks.
Thank you.
Thank you, Mr. Ayman. Is there any other question from our colleagues here who are attending? Please, if there is a question, you can go ahead and talk, because I cannot see the raised hand.
Yeah. Can we talk directly, Doctor? Yes, I think.
Fadal.
Okay, Assalamu alaikum. Thank you for this detailed introduction and presentation. Actually, it's the main question, the same question that my colleague asked. I'm working on using mainly advanced nonlinear techniques, mainly sliding mode control and backstepping controls. I just was asking about the feasibility of implementing these controllers here in your in the centers in KFUPM.
I mean, you want to implement the sliding mode control for
yes.
any microgrid system, or what
yes.
actually?
Yes,
Why do you want to?
For the same system, exactly. I'm working on DC microgrid control.
Okay. Yeah, definitely you can implement that any advanced control technique. This is I'm talking about, for example, decentralized control. You can use, for example, the non-linear control as a sliding mode control. I don't know much about this, but I think this is something non-linear control, right?
Yes.
Yeah, so you can use definitely. I saw one review paper that they reviewed. As you know, mainly this is where is the control actually? We have the control with this, this bidirectional converter. So whatever controller we choose, we can definitely apply this for this bidirectional converter to control either energy storage devices or for any buck or boost converter or buck boost converter. And I think definitely we can apply the sliding mode control. But I don't know what's the advantages. Is there any, advantages over the traditional decentralized control technique? I don't have idea about this. I mean, whether there is any idea for the sliding mode control.
Okay, let me grab the chance that Dr. Fahd is here. Is there any possibility for here, the student in KFUM, that if you have any summer internship or summer training in your centers?
Yes, we have summer training internship. Yes, however, you need to submit. Just send me email.
Okay.
What you are looking for, and we'll assess it. And there are different ways. Even there is what is called SURE program. We did it last summer for a few students. So just send me the email, and I'll give you the right direction, inshallah.
Good. Thank you.
Dr. Alam, there is a question also here in the chat. Can you elaborate more about the maximum point?
MPPT,
power point
maximum power
method?
Yeah, Doctor. If I see here for actually this, I will take some time for answering this question. Actually, for the DC distributed generation system, actually what I did, if I see here, I have considered a simplest model. I mean, we are emulating the PV system as a DC, but in real system, if we want to implement, for example, the PV system or wind system, definitely we have some. We have to implement the maximum power point tracking. I mean, the PV system, for example, it can provide the power, maximum power for a particular output voltage. So we have to control the voltage for the PV system. So we have to control the DC. I mean, this distributed generator, if it is PV, so in such a manner, it can provide the maximum power. But there is some problem. I mean, if we are operating the PV or the wind system in the maximum power point tracking algorithm, so it means that it is providing a maximum power and it does not have any, this called reserve power. But in microgrid balance, say for example, if it is islanded mode, if we don't have any other option, So some cases we may need to, operate the or the PV and wind system should participate also in, this balancing. I mean, they should have some provision of providing this additional energy or stepping or ramping up or ramping down the power. So this technique is called this is so far as I can remember, this is called deloading technique. So instead of operating the power at the maximum power point, we can operate it some reduced power point. So whenever we need, so that we can shift the power to the maximum, and we can also, I mean, we can have variable power from the PV system. So it will have, some positive impact on the system balancing, system stabilizing. Definitely, it will have some negative impact. I mean, where we are getting the maximum power, instead, if we operate it's some reduced level, so we have to have some cost. I mean, we will lose some energy from the PV system. So yeah, as you mentioned, that we can, we have to, operate the maximum power point, or any point below the maximum power point to have the reserve from the PV or wind system. I think I answered the question.
شكرا دكتور علم. Is there any other question يا شباب? Please, if you have a question, just raise it, because I don't have full control. So if you just go ahead and any other question يا شباب؟ طيب. If there is no further question, I would like again to thank Dr. Shafiul Alam. Thank you for presenting to us about DC microgrid, which is very important. It has overall good potential for new applications, especially with the smart meters, with the smart grid, and with the artificial intelligence. So there, I believe there will be a relatively big market as long there is good policies and regulation for relevant to microgrid and smart grid. جزاكم الله خير. Thank you again. Thank you, Dr. Shafiul Alam. والسلام عليكم ورحمة الله وبركاته.
وعليكم السلام. Thank you all for attending this presentation today. شكرا.
مع السلامة.
السلام عليكم ورحمة الله.
السلام.